Hi, this is Roger from Kanka Labs, and today it's about the usage of a Ferrite-Rod or loopstick antennas for the shortwave range. Now, you might know that loopstick antennas are heavily used in the long and medium wave range for reception. The reason for this is manifold. First of all, what you want to get when you build a Ferrite-Rod or loopstick antenna or any resonant magnetic antenna, you need a certain inductance to get the correct resonant frequency. And the inductance that you need in the medium or long wave range is relatively large. Standard is 170 microhenry for the medium wave range and 2.2 millihenries for the long wave range. When you couple these inductances with a 500 picofarad capacitor, then you get the right tuning range for the frequencies of the medium and long wave range. Now, getting an inductivity, a coil of that big or large inductance, you either, when you wind the coil in air, you get a very large antenna, either many windings, even up to several thousand if you have a small diameter, or you go to the concept of a frame antenna, which can have diameters in the meter range. Well, then you need less turns for your coil, but of course you have a very large diameter. And to get away with either a very large diameter of your coil or many hundreds or even thousands of windings or turns, the idea is to use a ferrite material, because you can imagine it that it kind of amplifies the inductance of a coil with a factor that is called mu or mu-r, the relative permeability of the ferrite material. And there is another advantage of ferrite rods, not only that you get small reception coils with a manageable number of turns, but also the field lines of the magnetic field is kind of sucked into the ferrite rod. So you get nearly the same reception signal. The amplitude of your signal is nearly the same as if you would use a very large winding with a very big diameter. But of course there is also one or more downsides to the concept of using ferrite materials. One of them is that ferrite materials are not suitable for very high frequency. We will discuss this in a minute. The second is, of course, you always get losses in the ferrite material. And the third is that the kind of wire that you use when you go to higher frequency, then this Litz wire, which is usually or normally used for long and medium wave reception, becomes less and less suitable when you go to frequencies above 1 megahertz. The reason is that the so-called proximity effect takes over, and the advantage of Litz wire compared to a single strand wire that it has in the long and medium wave range turns into its opposite. Let's remember two things. A standard Litz wire is not usable for frequencies above 1 megahertz, which means if you want to go into the shortwave range, you cannot use Litz wire anymore. You can, of course, but your quality factor of your antenna will drastically go down. And the second is we have to watch out what kind of ferrite material we use, because not all Ferrite-Rod materials are suitable for frequencies above 1 megahertz. And now let's go into some details. What's the real reason between this Ferrite-Rod used for long and medium wave? And you already can see a little difference between these two ferrite rods. Not only the size, but the color is a bit different. This one here looks more black, and this is more a grayish tone. And you can already deduct that this antenna that we have in our shop, especially for shortwave reception, that it apparently is made out of a different material. But now let's go to the data book about ferrite materials and take a look at the reason why we must use the right material for the right frequency. So this is an excerpt from a PDF data book from 2001 about Ferrox Cube ferrite materials. Ferrox Cube was or is the brand name of Philips, now NXP, ferrite materials, and you can still download it from many internet sources. I don't know if Ferrox Cube or NXP is still active in ferrite materials. Anyway, the data book is very informative if you want to learn something about ferrite materials. And I copied the page for the material 3B1, and that is the material especially used for long and medium wave reception Ferrite-Rod antennas. And let's remember that it is made out of a manganese zinc ferrite material. This is the more black one that we saw here on the antenna. It's not exactly the Ferrox Cube type, but it's a similar type. And the interesting graph for us is this one. This shows the permeability of the material, mu, related to frequency. And what we can see is that the heavy black line here, that shows the so-called real permeability. It starts to drop at about 2 megahertz, so that this is the first indication of that the material is not suitable for frequencies above 1 or 2 megahertz. But what's much more important, that is this dashed line, which is here designed as mu s. I don't know how the two hyphens are called here, double hyphen. This is the so-called imaginary part of the permeability. And what interests us is that the losses due to the magnetic losses in the ferrite is nothing else, or at least proportional to the distance between the black line and the dashed line. So we can see here at 100 kilohertz, where the long wave range starts, we have a great distance. We have a logarithmic scale, and the distance is about 2 decades, which means that the losses are less than 1%, but from 200 kilohertz upwards to 1 megahertz, it starts to heavily rise. And even at 1 megahertz, we only have a ratio between the two of only about a factor of 20, which means the losses are already in the percent range. And 1 megahertz is not the end, but it's the middle of the medium wave range. And if you would go over to the short wave range, which starts at 2 or 3 megahertz, then you can see the losses are just as large as the main inductance itself, or as the main permeability itself. So we can see this material really is only suitable up to 1 megahertz, or perhaps up to the end of the medium wave range, which is around 1.5 or 1.6 megahertz. Then the losses just become too large, and losses mean that the Q factor of your antenna drastically drops. And now let's compare this with the other material 4B1, and that is exactly the material that our special Ferrite-Rod for shortwave reception is made out of. I already mentioned the lighter gray color of this material. Now we can see it's a different kind of ferrite. It's a nickel zinc ferrite. And what we see now in the graph is that the real part of the permeability starts to drop at around 10 megahertz. That's nearly a factor of 5 better than the other material we saw beforehand. But nevertheless, the losses also start to rise from 1 megahertz upwards. So I would say that the maximum useful range is around 10 megahertz that this material can be used. Even there you have heavy losses in the range of 10 or 20%. But it should be good for the low shortwave bands. Let's say between 2 and 5 megahertz. That is what I would say is the main application where we can use this material for winding a Ferrite-Rod antenna. And so now we still have to look out for what kind of materials do we use to wind such a coil, and what else do we have to regard when using this material for a lower shortwave band's loopstick antenna. So in every good Ferrite-Rod antenna that you see, you will notice that the reception coil, or coils if there are more than one, are not wound directly onto the Ferrite-Rod, but there is always a kind of carrier material that the winding is wound on. The reason is manifold. First of all, by using a material as a kind of spacer, you can easily shift and thereby fine-tune the coil, because the inductance that you get is also sensitive to the position of the coil. You get the largest inductance when you place the coil in the middle, and you get an increasingly or decreasingly smaller inductance when you shift the coil to the side. The second thing is the protection of as well the ferrite material and the Litz wire, or whatever kind of wire you use, because ferrite material is not only very brittle, it cracks immediately if you let it fall on the floor, but there can be also some very sharp edges, and that would break injure the insulation of the wire that you use. And even the other way around is possible by winding by using a wire like here, this one here, like enameled copper wire. or magnet wire. You could even, by winding very close or making a very firm winding, you could even break the ferrite material. So that is the second reason why you never should wind a winding for a reception antenna directly onto the coil. But the question is, what material do you use? Well, in former times it was often cardboard used. Here it is apparently plastic. But the material itself can be a factor of dielectric losses. We already know we have magnetic losses in the ferrite material because the magnetic field from the wave that comes into the electromagnetic wave, it has to constantly reorientate the magnetic material inside the ferrite-rod. And let's take the medium wave range. There it is, 1 million times a second. The direction of the field changes from north-south to the other way around. And every change of the magnetic field, there's some energy loss because reorientating the magnetic domains in this material just sucks up energy. And these are the magnetic losses, but you know, every insulating material like cardboard or plastic also has losses, and these are electrical, or better say dielectric losses. And you know this from capacitors, that they're, for example, Teflon or PTFE or polypropylene are the best or one of the best plastic film materials with the least losses. And while other materials like, for example, PVC, which is often used as insulation for mains wire cables, is one of the worst materials. So which material should we choose? We should not choose any plastic. If we get some Teflon or polypropylene foil, that would be good, but it's not easily available. But the next best thing is simply cellophane, which is still used for packing food. You should be sure that it's really cellophane foil or film, and this is relatively good dielectric materials. So the first thing we should do, we should put at least one layer of cellophane film around the ferrite-rod to protect the ferrite-rod and to protect the winding that we want to put on. And next is what wire do we use? Well, you already can see it, and I already mentioned it. Never use Litz wire for shortwave reception for anything above 1 megahertz. In that frequency range, proximity effect and skin effect take over, and there is only one remedy. We should use the thickest magnet wire or enameled copper wire that we get, that still gives us enough place for the winding. And the last part of the recipe is the distance between one turn to the next should be at least 6 times the diameter of your wire. So here I have 1 millimeter diameter magnet wire, and we will make a test winding and measure the inductance and see if we can also calculate the inductance from the data sheet and from my Excel file that I made just for calculating different kinds of magnet antennas. So this is the end result of our test coil. You can see that I've put the cellophane paper around as a protection, and you might also notice or have asked yourself, well, how do you get the coating off from the enameled copper wire? Well, I already did a video on this little tool from Knipex with which you can strip the coating quite easily off, even of heavily or very thick copper wire. And you might notice that the ends here are now quite shiny and are really the blank copper. And we can count 1, 2, 3, 4, 5, 6, 7 turns. Now let's remember this, 7 turns. Now we connect it to our LCR meter, which I will show you in a second so that you can read the display. And we get 3.37, let's round it up to 3.4 microhenry. And now let's do some calculations and try to find out if this result matches the calculated inductance from 7 turns on this Ferrite-Rod, specially for shortwave reception. So here I've listed the measured values. We got a measured inductance of 3.4 microhenry. We had the number of turns was 7. The length of the winding, that is from first winding to last turn, is 85 millimeters. The Ferrite-Rod itself has a 150 millimeters length and 8 millimeter diameter. That way the diameter of the winding is of course also 8 millimeter and something. We would have to take the wire diameter still into account. So basically we make this 9 millimeter because we have a 1 millimeter diameter magnet wire. And the relative permeability of the material according to the data sheet is 250 plus minus 20%. So, but there's still one important factor when trying to calculate from these values. We could, in theory, calculate the inductance that we already measured, but when using ferrite rods as magnetic material, there is still one important factor, and that is the aspect ratio of the ferrite rod, or the length to diameter ratio, which you can see here on the x-axis. And we already saw we had a ferrite rod with 150 to 8 millimeter, that is nearly 20. So let's take this curve, the length to diameter nearly 20. And now we have an initial permeability of around 250, but you can see, let's take here the curve for 200. This drops down to around 100 or a little bit less. So obviously we cannot take the full permeability of the ferrite material due to using a ferrite rod with a length to diameter ratio of nearly 20. We have to reduce this from around to half of its value, from 250 to 100 or 125, something like that. So let's take this into account, and let's say that in our Excel spreadsheet we use only 120. And now let's put these values into our Excel spreadsheet and see if we really get also a calculated value of inductance of 3.4 microhenry. There are still some more factors that have an effect on the inductance. As I already mentioned, it's just the position of the coil on the rod. And here we have spread the winding from over a quite substantial part of the ferrite rod. So here in the middle we have a greater permeability than at the end, so we probably will even have to use a still smaller value than 120, because the graph we just showed, where we took this reduction factor or this reduced permeability, is basically only valid if the winding is concentrated in the middle of the ferrite rod. But let's see if we put the data into the spreadsheet and see if we can get a value anywhere near 3.4 microhenries. So what I already prepared is I just as a guess took a frequency of 4000 kilohertz, or in other words 4 megahertz, with a 500 picofarad capacitor, and therefore we would need something in the range of 3.2 microhenries as a inductance of our reception coil. Now, here we have the mu r that we just saw was at best with our shortwave ferrite rod 120. The winding diameter we said was 9 millimeters. The length of the winding we said was, we measured was 85 millimeters. We have a circular winding, and it would tell us we would need 5.4 or rounded 5 turns to get 3.2 microhenry. Well, that's relatively near to our 7 windings that we made. In fact, let's twiddle around a little bit with the figures, with the numbers, to get to get somewhere near the value that we seek. Now we have a target inductance of 3.5, and therefore we need, that is quite near to the measured value 3.4, and therefore we would need 5.7 turns. So obviously the mu r is still smaller, and it's even smaller than 100. Let's even go down to 75. Now with 75 or with 80, with a mu r of 80, we in fact get the 7 turns. So we now know by playing around a little bit with the numbers that our initial, or the permeability of our material, which is 250, is reduced down to around 80 when we wind a coil on this special shortwave ferrite rod with 150 millimeter length, 8 millimeter diameter, 9 millimeter winding diameter, 7 turns stretched out to 85 millimeter. So you can see it's better not for this kind of application not trying to calculate the necessary inductance or the number of turns that you use, that you have to wind when trying to wind a loopstick antenna. It's better to make a test winding and increase or decrease the number of turns, and always measure the inductance with an inductance meter, an LCR meter or whatever, until you get the desired result. Simply because this important factor, the relative permeability, not only of your material but of your special ferrite rod, it depends on so many factors. It depends on the diameter, the aspect ratio, the length of the winding, etc., etc. So that only with a test winding you can get a correct result, and from that result on you can do better calculations. But the final verdict is, for ferrite rod antennas, do not use a spreadsheet or a formula to try to calculate the numbers. Make test windings and change the winding as long until you get the final desired inductance for your application. So that was it for today. A little bit in theory, about theory and practice, about what you have to take care of when using or trying to use ferrite rods for the lower shortwave band. To sum it up, you have to use the right material. For example, the readily available ferrite rod that we sell in our shop, especially for shortwave applications. Good usable up to 5 megahertz, and with perhaps until 10 megahertz, but then already with losses. Use thick enameled copper wire or magnet wire. Thick means 1 millimeter at least in diameter. Stretch out your windings not to get the proximity effect come into place to ruin your Q factor. And when you use all these parts of the recipe to make a high quality, high Q factor shortwave loopstick antenna, then you finally get a decent result in a small volume, and with all the other advantages that magnetic antennas have. You have a directional sensitivity, you have a small antenna, and well, yeah, that was it as a summary. Thanks for watching. If it was interesting, give it a big thumbs up, and see you next time. Bye from Roger. Bye from Kanka Labs.